Welcome to Senior High School Math Series. This time, let us have the principle of mathematical induction, and this is part 2 of 3 parts under PreCalculus. During the first part of this presentation, we applied the principle of mathematical induction in proving statements involving series. The link to that video is on the description of this video. This time around, we're going to apply mathematical induction to prove a property of divisibility. Before we continue, let us have a recall of important concepts. If P and Q are integers and Q is not equal to 0, then Q is a factor of P if and only if P is equal to C times Q for some integer C. Similarly, if P of x and Q of x are polynomials, and Q of x is not the zero polynomial, then Q of x is a factor of P of x if and only if there exists a polynomial C of x such that P of x is equal to the product C of x times Q of x. These ideas from the previous slide may be used to prove the factor of a polynomial sum theorem and the transitive property of polynomial divisibility, which are briefly stated as follows. For all integers and polynomials x, y, and z, if x is a factor of both y and z, then x is a factor of y plus z. Also, if x is a factor of y and y is a factor of z, then x is a factor of z. The first of these two properties will be seen in our first example. Let us have an example. Example number 1. Prove that 2 is a factor of n squared plus n for every n element of positive integers. In here, our statement S of n is that 2 is a factor of n squared plus n for every n element of positive integers, or simply natural numbers n. Let us have the basis step. We're going to prove that S of 1 is true. Hence, we're going to substitute n equals 1 to n squared plus n. Then we will have 1 squared plus 1, and that is equal to 2. And clearly, 2 is a factor of 2. Therefore, S of 1 is true. After the first step, we proceed to the second step, that is the inductive step, that is when n is equal to k. In here, we're going to show that the assumption that S of k is true implies that S of k plus 1 is true. The inductive assumption S of k is a statement 2 is a factor of k squared plus k for some particular but arbitrarily chosen integer k greater than or equal to 1. That is when n is equal to k. From here, we're going to show that S of k plus 1 is true. Hence, the statement S of k plus 1 is that 2 is a factor of k plus 1 squared plus k plus 1. That is when n is equal to k plus 1. Expanding the expression k plus 1 squared, we will have k squared plus 2k plus 1, and then we still have k plus 1. We're writing this expression. We have k squared plus k plus 2k plus 2. From the inductive assumption, k squared plus k has a factor of 2, and the remaining terms in the sum, 2k and 2, both have a factor of 2. By the factor of an integer sum theorem, 2 is a factor of k plus 1 squared plus k plus 1. So, S of k plus 1 is true. From steps 1 and 2, using the principle of mathematical induction, 2 is a factor of n squared plus n is true for all integers n greater than or equal to 1. Let us have example number 2. Sometimes it is helpful to add and subtract the same quantity during a proof in order to show that an expression is factorable. That is what we call the adding and subtracting technique. Prove that 8 is a factor of 9 raised to n minus 1 for all natural numbers n. In here, our statement S of n is that 8 is a factor of 9 raised to n minus 1 for all natural numbers n. For the first step, we're going to show that S of 1, that is when n is equal to 1, is true. Hence, the statement S of 1 will be 8 is a factor of 9 raised to 1 minus 1. 9 raised to 1 is 9 minus 1, that is equal to 8. And 8 is clearly a factor of 8. Therefore, S of 1, or the basis step, is true. After the first step, we're going to proceed to the second step, that is the inductive step. First, we're going to assume that this statement S of k, that is when n is equal to k, is true. 8 is a factor of 9 raised to k minus 1 for all particular but arbitrarily chosen natural numbers k greater than or equal to 1. From here, we're going to show that the statement S of k plus 1 is true, and that is 8 is a factor of 9 raised to k plus 1 minus 1. From the rule of exponent, 9 raised to k plus 1 is 9 times 9 raised to k. Then we have minus 1. This is the point where we are going to add and subtract the same quantity to the expression. So we will have 9 times 9 raised to k minus 1 plus 1. Since adding and subtracting 1 to the expression, 9 raised to k would mean adding nothing. Hence, the value of the expression is not changed. We still have minus 1 outside of this quantity. By distributive property, we'll have 9 times 9 raised to k minus 9 plus 9 minus 1. By grouping terms, we will have 9 times 9 raised to k minus 9 as one group and 9 minus 1 as another, and this will not change the value of the expression. From the first term, we have 9 times 9 raised to k minus 1, and 9 minus 1 is equal to 8. The inductive assumption states that 8 is a factor of 9 raised to k minus 1. That is, this statement S of k is true. Since 9 raised to k minus 1 is a factor of 9 times 9 raised to k minus 1, by the transitive property of integer factors, 8 is then a factor of 9 times 9 raised to k minus 1. Since 8 is also a factor of itself, by the factor of an integer sum theorem, 8 is a factor of 9 times 9 raised to k minus 1 plus 8. Therefore, 8 is a factor of 9 raised to k plus 1 minus 1. And so, S of k plus 1 is true. From steps 1 and 2, using the principle of mathematical induction, 8 is a factor of 9 raised to n minus 1 for all natural numbers n. That will be all. Thank you for watching. Please subscribe for more math lessons.